Hi there, my name's Joel Brogan, and I'm going to talk to you about fast local spatial verification for feature-agnostic large-scale image retrieval. This is a joint collaboration between the Computer Vision Lab at Notre Dame, Unicamp, and Oak Ridge National Laboratory. This paper will be published in the latest issue of IEEE Transactions on Image Processing. So let's get to it. What is fast local spatial verification for feature-agnostic large-scale image retrieval? Well, it doesn't roll off the tongue, that's for sure. But really all it is a fancy way of saying specialized image search. Kind of like this, except maybe not for horses. No, instead we're just going to be running with normal images for this one. So, on the internet these days, if you find one nice image, you're bound to have found 1,000,001 people who want to create different types of modifications to it. It doesn't matter what kind of modification, any'll do. We need search algorithms that are tailored to these particular types of modifications, in which pieces of the image are cut and pasted into other composites. So we proposed a new type of image search problem, which we named Objects and Scenes to Objects and Scenes, or OS to OS for short. So, what is OS to OS? We'll take this image of a nice dog having a nice picnic in a nice park. Well, there's 3 types of related images to this particular image. We'll call it query Q, and there's match A, B, and C. Starting on the right, match C has an entire background that matches with the image. Match B contributes a small portion of content to the query, while match A borrows a piece of content. We call these the host, donor, and borrower respectively, and we want an image algorithm that can search and retrieve all 3 of these types of relationships. To make matters even more difficult, a lot of times there will be many instances of borrowers, donors, and hosts in a single query image. For instance, let's take this one. There are 2 host images in this particular image. One is the background forest, which we see here, and one is the image with the woman swinging. Then, there are about 14 other smaller contributors to this particular composite. If we were to use this image as a query, we'd want an OS to OS search algorithm to go out and find all of the original content donors and content borrowers that are related to this particular image, including the hosts. So how would you do that in practice? Well, in a traditional search image pipeline, you'd take a query image, find all of its particular features, which we like to call local features. We'd extract information from them all and query them into a database that's filled with more local features. Now this database would then be able to return to us the number of local feature matches with other images that are in the database. So, for instance, we'd expect to find a lot of local feature matches between the query image and the image of just the background forest. Maybe some more for another forest that looks similar, and even more for this particular woman on her swing. However, for all of the other smaller contributing objects, they get a lot lower scores because they're much smaller in the image, so they don't get nearly as many features and therefore not as high of a number of matches. Well, with OS to OS, we want to take the results in green here, which are correct, and raise them up while suppressing the results in red. So we push down rank number 2 result and bring up all the rest to make it look more like this in the end, because all of those little contributing objects are significantly more important than that image of an arbitrary forest that we don't need. So maybe you're just saying, well, that's an easy fix. We could just use an object detector and search all of the objects that it finds one by one into an image database. Well, wrong. That's slow. We propose OS to OS spatial scoring. This is a multi-part type of re-ranking algorithm which first takes the local features and partitions them based on which images they belong to in a given set of results. We then take those partitions and use them to find a focal point. After calculating this focal point, we use it to reproject the features relative to their locations in the query image. Once the features are reprojected, then we cluster and score them at the very end. This could be thought of a lot like the generalized Hough transform. However, there are a few key differences. So let's move on to a concrete example with some whales. For those of you following along at home, this is where the two whales share overlapping content in the images. Now, let's first find our local features and match them up. Then we'll calculate our focal point, or centroid, and we'll project all of our query features relative to that centroid. We can then take those projection vectors and apply them to the same features on the match, and we get something that looks like this. Unfortunately, since the match has a rotated portion of the image pertaining to that whale, they look all over the place. So we need to add in another step. We calculate, using wavelet responses, the angle of each particular local feature. In this case, about 51 degrees or so, because it's a nice straight line. Now, this isn't tough to do. In fact, it's included in most local feature implementations, such as SURF or SIFT features, and can be easily implemented for whatever other type of feature you would like to use. Once we get all of these calculated feature orientations, we do the same thing for match P, and then we subtract them to find the difference between the features. Once we find this difference, we can apply that difference as a rotation to all of the vectors, and bada bing, bada boom, you have a new feature accumulation matrix. It looks something like this when you start to plot it out as a heat map. That area of dark red means that we have a high probability for a partial image match candidate in that area. Now, this particular algorithm is very robust to stretching, perspective transform, affine transform, and rotation. Furthermore, you can take the algorithm and extend it to use an entire match matrix of different images and their respective local features. And using that match matrix, you can create tensorized feature calculations that allow you to greatly accelerate the re-ranking process using GPUs and libraries such as TensorFlow, NumPy, or CuPy. Using this type of acceleration, we can see that our algorithm runs in relatively linear time when plotted over the number of features that we retrieve, and works much faster than other algorithms that do similar types of spatial verification. Additionally, we can use deep features with it, such as the deep local attentive features from Google Labs, also known as DELF, and insert them instead of the other local features that we were talking about before. Using this type of approach, we see on the Oxford and Paris datasets that the algorithm performs very comparably to other state-of-the-art algorithms in the field. And additionally, in the NIST MFC 18 dataset, which contains a lot of composite images, we find that it performs not only better on the total recall of the dataset, but also the donor-only recall of the dataset, which is retrieving only those donor-related images. Then on the Google Landmarks dataset, we see again that our algorithm keeps up and even outperforms some of the other algorithms like DELF or deep image retrieval by just including this OS to OS component. Here are some nice, pretty qualitative results if you'd like to see them, but go to the paper for more if you'd like more information on how it all works. And thanks for watching. I hope you had a good time.